So today we're finishing off Chapter 9. When we come back on Monday, we'll start in on Chapter 10, which is on vibrational motion. And that takes us towards sort of the end of this course. Vibration and waves is how we'll end up. This is just to show you that inside every iPhone is a tiny little spinning gyroscope. And in fact, it doesn't just spin in one direction, it flips back and forth. It looks like this, and it's attached to all these little springs. This is sort of a schematic of how it's supposed to look. And this is an electron microscope image of an actual gyroscope that goes into a phone. And it's very, very tiny. It sits in the center of this chip. And there's all these little sensors on the end of it, so that if you change the rotation axis by changing the orientation in space of your iPhone, then these detectors will know it, and it will allow you to find how your iPhone is oriented. Okay, so test 2 was marked. There's the distribution. The average was 64%, which was quite a bit, so I think this was quite a bit of a harder test than test 1. I think that's partly because this is more difficult material. You're getting into conservation of momentum, conservation of energy, and so, but also I think it was a harder test, and I don't think that's totally fair in the sense that you'd like the first test average to be sort of similar to the second test average. Some people were ill for one or the other, and when that happens, the one that you were well for counts for both and stuff, so if one is different than the other, that's bad. So anyway, what I decided to do was to boost up the marks, and so we did this breakpoint scheme. So if you got 0, you got 0, so there's no boost. If you got 100%, you got 100%, there's no boost. If you got 50%, you got a 15% boost. And then it's sort of, there's a linear interpolation between this. So if you got, for example, 25%, you'd get a 7.5% boost. If you got 75%, you'd get a 7.5% boost, etc. There were, just plug this in. There were 2 people who didn't get any boost at all. There were actually 6 perfect scratch cards we found, which just looked pristine and beautiful and no scratching except right on the right answers. And maybe about, I think there's about 640 students in this class, so about 10% got an A+. You should look at your test. It should come back to you in practicals. If you find there's any mistake in the marking, then we will definitely fix that. Just give us a shout by December 3rd and we'll fix it up for you. So that's it about that. So the next thing I was going to do is go on to finish off Chapter 9. So how are we doing? Is there any questions about the midterm? Is everybody comfortable? If you're in the video overflow room, come on down. There's tons of seats. This is an almost half-empty room. Yes, question?
Mark that appears on Fergus is the one that has the breakpoint.
Yes, that's an excellent question. And when people come down a little bit, I'll answer that one. I'll repeat it and answer it. The question is, which one of these is displayed on Quarkus? And that's a great question. The Quarkus gives the higher mark, the mark we're going to use. So it's the adjusted one. Okay? So the raw mark that you see that you can compute yourself will not be the one that's posted on Quarkus. That's a good question. Anything else? Any other questions? Okay. So we talked about the stability of rotating objects. Basic idea there is that if something doesn't have any rotational momentum to it, then a little torque by gravity is enough to tilt it. If you give it a little bit of rotational momentum, and you can use your right hand to figure out which way that is, it's a little bit to the right in this case, then it's a little bit of gravity will tilt it a little bit, but it wants to straighten itself out. And the faster it goes, the more the rotational momentum is, and so the torque of gravity does less and less to actually change that. So that is actually why it's, I don't know if you've ever, I've taught lots of kids how to ride their bike, and the idea with kids is that, okay, go as slow as possible. But in fact, with bikes, you have to be going kind of fast in order to get that stability and to make it easier to ride it. So the faster the person riding the bike, the greater the rotational momentum vector, which is in this case out to the left as viewed from above. And then the system is more easily balanced from the torques of gravity. So on that kind of bent, since we're talking about changing L, let's do this question. So a person is spinning a tennis ball in a string in a horizontal circle. Okay. And it's going, I guess, clockwise, counterclockwise as viewed from above, and the z-axis is up. So it's spinning in the xy plane. And you give it a little boost, which I guess is coming from a torque. In what direction will that change the rotational momentum of the tennis ball? X, Y, or Z? So I'd like you to think about that, and then you can pair up, share with your neighbor, and click it. Think, pair, share. And stop. So what's going on here? You've certainly, I guess, increased its linear momentum in what looks like to be the x direction. But what I'm thinking of is that this is somehow, where's my pen? A change in the rotational momentum. You've increased omega. So which way is omega? You have to use the right-hand rule to do that. So I would say this is going to be in the plus z direction. If you use the right-hand rule, this is how you had to solve this one, then your fingers are curving in this direction, and again I have to draw a hand. Stop laughing at my drawing. It's just I'm terrified that it's crude or something. But anyway, so you're spinning this thing above your head. It's going like this. So instead of a tennis ball, I have this orange piece of tape that's going around. But it's a particle on a rotating object, isn't it? Is one way of looking at it. It has rotational momentum. It has rotational velocity. It has rotational momentum. And if I speed it up, it doesn't matter if I hit here, 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 here. I'm going to increase the L vector, the angular momentum, in the plus z direction. And if I slow it down, it'll decrease that. So dl will be down. Okay. Question? Does that seem okay? It was a right-hand rule question in disguise. Okay. So, rotational momentum of an isolated system is constant. So if the net torques are 0, then if there's a change in rotational inertia, then it has to be accompanied by a change in this angular speed, because the product of rotational inertia times angular speed is going to be constant. And this is what I was trying to demonstrate when I held those masses out, and when I decreased I, had to increase omega. But there are problems that use this. So why don't we do one of those? Okay, why I press switch. Press zoom a little bit. So you can see that. A 20 centimeter diameter, 2 kilogram solid disc is rotating at 200 RPM. So let's draw it, initial. I'm going to draw it down here, actually. Here's the disc. I'll label it as the disc. And its initial, and I'm going to call it object 1, because there's going to be an object 2, is equal to 200 RPM, revolutions per minute. A 20 centimeter diameter, 1.0 kilogram circular loop, so we can put a loop up here, is dropped straight down onto the rotating disc. So this one's rotating around, and this initial loop, so I'm going to call this object 2, is 0. Friction causes the loop to accelerate until it is riding on the disc. What is the final angular speed of the combined system? So the final situation is that they're stuck together. I'll try to draw that. And they're both rotating with some angular speed omega final, and that's what we're trying to find. So what I'm going to do is assume that this is a totally inelastic collision. So that some energy goes away because of friction when they collide together, but they stick together at the end, and they're moving with the same velocity. So this will conserve angular momentum in elastic collision. And this is going to angular or rotational momentum is conserved. Okay? So I'm going to say that L final equals L initial. And I'm going to use that L is equal to I times omega. And the other equations I need is that for a disk, we've got I is equal to 1/2 m times r squared. And for a loop, you need I is equal to m times r squared. So those are, I think, all the equations I need. Now I can solve it. So it's L final equals L initial. So the initial situation, I'll put on the right here, is that you've got the disk is rotating. So it's going to be I of the disk, which is 1/2 m1 times r. And by the way, they both have the same value of r, so I'm going to say r1 equals r2 equals r, which is the 10 centimeters. So they have different masses, but they have the same values of r, so I'm just going to put r squared here. Times omega initial 1. That's the disk initial, and then plus the loop, which is not rotating. So it has 0. And then finally, they're both rotating together, so what we're going to have is, I guess, the sums of their two rotational momenta. So I can say something like omega final times their 1/2 m1 r squared plus m2 times r squared. Okay. I'm going to divide both sides by r squared. Turns out not to matter, because every term that's not 0 has an r squared in it. And I'm also going to use the fact that m1 is 2 kilograms and m2 is equal to 1 kilogram. So I end up with 1/2 of 2 plus 1 times omega final is equal to 1/2 of 2 times omega initial 1. Solving that all out, I get omega final is equal to omega initial 1 divided by 2. It's 200 RPM divided by 2. It's 100 RPM in this case. Just goes down by half. And I guess they've just made the numbers work out that way. And what's interesting here is that there's no need to convert to SI. You could if you want to, But if you look, I didn't at any point multiply by a torque in like newtons times meters. I didn't actually use those kilograms. I ended up doing ratios. So at the very end, I just knew the omega final was half of whatever omega initial was. And so I just kept it in the bad units to save a little time. Yes, question?
Are we dividing both sides by r squared because they both have the same?
Exactly. The only reason you're allowed to do that is because they both have the same radius. And so this should have been r1 squared, and this was r2 squared and r1 squared, but they were all the same, so I was able to divide both sides. That's a really good point. Okay. I'm going to switch back, I think. Any other questions? Okay. Another tip which I've just put down on here is that rotational momentum is sometimes called angular momentum. You've probably heard me sometimes use that word, so it's from your text. Okay, and now this is the last of the analogies from this chapter. It's just rotational kinetic energy. And it has a very familiar looking equation. Remember, kinetic energy is 1/2 mv squared. This is 1/2 I omega squared. So if we want to go to that chart with all of our analogies, we'll do that in a second. So this is just showing what rotational kinetic energy can do for you. The textbook talks about flywheels, and what you can have is a spinning flywheel, like a big heavy disc, inside your car. And they have braking systems for some cars, some race cars, where instead of the brake pads just rubbing against each other and converting your translational kinetic energy into heat, you can hook it up to a flywheel so you convert your translational kinetic energy into spinning the flywheel even faster. And when you do that, you can reverse the process and have, when you step on the gas again, have that flywheel kinetic energy go back into the translational kinetic energy of the car. It's a way of giving yourself an extra boost using your brakes. Let's do this question. I had a chart coming up, but let's just think about this equation for a minute. I think I'll write it up on here. The equation was rotational kinetic energy, K rotational, is equal to 1/2 times I times omega squared. And what was happening with the figure skater is that she starts off with a somewhat larger rotational inertia, and I don't have an equation in my book for this because I don't know what she is, a cylinder with some more rods going out or something. I don't know, I don't even want to model it, but I know it's something in kilograms meters squared, and when she brings her arms in, more of that mass is towards the center, towards her, or closer to the rotation axis, so that rotational inertia is less. The closer the mass is to the rotation axis, the smaller the rotational inertia, so she has to increase her omega. So my question is, what does that do? We know that rotational momentum is conserved. What does it do to rotational kinetic energy? I'll give you a minute to think about that. Pair up and share with your neighbor. So please take a stab at it, and then I'll tell you what I think. 5, 4, 3, 2, 1, and stop. So this is not at all obvious. So what I do think is that L is equal to I times omega is constant, assuming that there's no external torques. So you neglect the friction from the skates. So now what I'm going to do is try to combine these two equations. I can say that K rotational, which is what we're asked about, is equal to 1/2 times I times omega times omega. All I've done is take the omega squared and changed it into omega times omega. And now I'm going to put parentheses around this. See where I'm going with this? And now I'm going to say that the rotational kinetic energy is equal to a half, which I know is constant, times L, which I know is constant, times omega, which I know goes up as she pulls her arms in. So as omega goes up, I think the rotational kinetic energy must also go up. Now this is very surprising to me because I don't know what work is done on her, but I think she must be doing work on herself. She's pulling in her arms. That must take energy to pull her arms inwards. And so that energy is coming from the breakfast she ate that morning and being converted into rotational kinetic energy. It's not external work. It's sort of, she's doing work on herself. It's one of the amazing things about physics. With no net external force, you can still do work on yourself. How you guys feel about that? Okay? It's a tricky one. Oh yeah, this was that promised chart. It's really ridiculous, but let's go through it. Yeah, so all the things on the left are the old things that you learned before, the linear stuff, and all the things on the right are the Greek, the new things of this chapter 8 and chapter 9. So what we had was position, velocity, acceleration. We have angular position, angular velocity, angular acceleration. The rotational and analog of force was torque. The rotational analog of mass was this rotational inertia. These have different units, so force, so all these ones go to radians. Force goes to newtons times meters for some reason. Mass goes to kilograms times meters squared for some reason. And when you do all that, you get Newton's second law, which used to be the acceleration is force divided by mass. Now you got the angular acceleration is the torque, net torque, divided by rotational inertia. And now we've got kinetic energy. Okay, we're going to call this translational kinetic energy because the object is translating from one place to another, is 1/2 mv squared. And the rotational, if it's also spinning around its center of mass or something, it has rotational kinetic energy of 1/2 I omega squared. Where I is now that rotational inertia around that center of mass. And then lastly, this vector momentum P is mv. You've got L is equal to I omega. And those are all the analogies I'm going to do. Let's do an example of rotational kinetic energy. So the example is this. A 0.5 kilogram basketball rolls along the ground at 1.0 meters per second. What is its total kinetic energy? And it's asking for translational plus rotational. So we can sketch it. There's the ground. Here's the basketball. It's moving along at v is equal to 1.0 meters per second. It has a mass is 0.5 kilograms. It's rotating, so it's going to be, we're going to here assume that it's rolling without skidding. So remember that when you have the rolling without skidding assumption, it gives you those three equations. S is theta times r, V is omega times r, and A is omega times alpha or something. The one that's important for us in this case is that V is omega times r. That's going to be useful later, I think. What we're trying to find here is K is equal to K translational plus K rotational. And the other thing we're going to need is that We have to find the basketball. Oh yeah, it says right there. It's going to look it up. It's right there. So we're going to use this. This is a hollow shell. It's 2/3, which is really what a basketball is. It's rubber and it's filled with air, and the air doesn't weigh as much as the rubber. Okay, so let's simplify and diagram whatever. It's K is equal to 1/2 m times v squared plus 1/2 I times omega squared. I think what I'm going to do is leave this one and try to sub in all the things that we know for this. So from our rolling without skidding constraint, we've got that omega is equal to v divided by r. So I'm going to sub that into here, and I'm going to take this equation and sub that into here. So, and I'm already sort of on the represent mathematically step, so I'll just sort of, well, we'll put it right here, I guess. So K is equal to, we'll keep the 1/2 mv squared. Are we good? Plus 1/2 times 2/3 times m r squared times v over r all squared. So that is equal to, again, 1/2 mv squared. 2 times 1 is 2. Through 2 times 3 is 6, so it's 2 over 6 times m times r squared times v squared divided by r squared. So this is another one of these weird cases where the r's cancel. And I guess that's good because I was starting to wonder what the radius of a basketball was, which is easy to Google, but it doesn't actually give it to you. So anyway, let's just say, yay. I like it when things cancel. I do a little celebration every time. So this is the total kinetic energy. I don't know, you can just, so it's equal to, and what's interesting is that now you've got 1/2 of mv squared plus 2/6 of mv squared. So you can kind of lowest common denominator it. It's equal to, K is equal to 3/6 plus 2/6 all times mv squared. So it's equal to 5/6 mv squared. So K is equal to 5/6 times 0.5 kilograms times 1 squared, 0.42 joules. Any questions about that? Do you have any questions back there? You with the blue laptop? You're talking to your neighbor? Do you have a question, or you're okay with it? You guys okay with doing examples? It's, a lot of this is, you have to work through your mastering physics problems, get a pen and paper, try to work through these things, and you do get better at it. At trying to set up these diagrams. Yes, question, yes?
How would you evaluate this?
Don't ask me. You're right, I'm going to lose points if I don't evaluate. Well, okay, good question. So I would just say that it is split between, I guess, whatever, 3/5 translational and 2/5 rotational. Something like that. I think that's kind of interesting, isn't it? I thought maybe it would be 50/50 translational to rotational, but that's not the way it worked for the hollow sphere. It's very sad sometimes when I see Brian Wilson's marking scheme and I don't know if I would get 100% on it. Okay. Got to remember to evaluate. It is important. Okay. Let's sum up all the different kinds of energy that you guys have gotten in this crazy course. Ever since you met me, right, which was chapter 7, when we talked about work, we've been doing energy this, energy that. So we had kinetic energy, 1/2 mv squared, which we've now changed its name to translational. We have mgy, the gravitational potential energy. We have The spring, if something has a spring in the system, then there's 1/2 k times x squared. There's going to be springs coming back, by the way, next chapter, so be aware of that. And again, any questions? You two ladies right here, do you have any questions? Are you interested in this? Because if you're talking, all the people around you are struggling to hear me. But if you have a question, you'd like to address it, I would love to hear it. Okay? Sorry to single you out. It's all the buzzing that's distracting for me. Rotational kinetic energy now, this 1/2 I times omega squared. Remember, internal thermal energy, that had an equation for it, which was usually the kinetic friction, mu sub k times the normal force, times whatever the displacement was, how far it was rubbing. You got a positive internal energy. And if you have one system, the system has the sum of all of these energies. And sometimes it's 0 because there's no spring or something, or it doesn't change its y position. But you have to add these all up if you're going to do a conservation of energy problem. Unless you put work into or out of the system, you can do that using work, and the work is the force times the displacement times the cosine of the angle between the force vector and the displacement. Okay, let's do this. So what we're going to do is, whoa, okay, slow down. We're going to have a vote. So I'm going to do a race between this disc, it's going to roll without slipping, versus this hoop, which is going to roll without slipping down the same incline. We're going to use the same incline. We're going to start them right side by side, let them roll, again, without slipping, and see which wins. And what I'd like you to do is think about all the things you know about rotational kinetic energy. They're both, they both have to have some omega, which is related to their velocity. And try to predict which should be the winner. They're going to roll by gravity. So think about it, pair up and share. And if you want to continue your conversations, this is a great time for the next minute. What? Let's stop. And then let's check it. Marks cassette, go. The moral of the story being that nature is not a democracy. It's a dictatorship of Mother Nature, whoever is setting the rules to this place. So the question is why? We have to think about this, and I think it's something to do. Certainly this has more of its, I guess it's got a larger rotational inertia per its mass or something like that, right? And what's weird actually too is that this says 677.6 grams, and this was also ground to be 677.6 grams. And so they've made these two objects to have the same mass. So this really does, the only difference is it has larger rotational inertia. And you can even do it with these two cylinders. So these are two cylinders. They're exactly made of the same material even, and they have holes cut out of them, 4 holes. And so this one has a larger rotational inertia than the other one. And somehow that larger rotational inertia just slows it down just a little bit. So it's B. And I'm going to come back to this in a minute, but let's do a simpler question first. And I got it on deliver now, hopefully. Yes. So you can see it. So now we're going to have a race between now this is a thought experiment because Pius was not able to give me a frictionless. It just, okay, in this case, it's like, who wins? Okay, so let's just pretend for a minute that we were timing something that was on a frictionless incline versus something that was rolling down a frictiony incline. So maybe there was 2 inclines, one perfectly frictionless and one with friction side by side. Which one, the block or the disc wins? Okay, this was very, very split. I'll show you what I think. So I'm going to go through this twice. One in just a sort of conceptual energy way, and then I'll also just do it mathematically. This is pretty easy to figure out. But, well, let's do it through it. So the first thing is, I told you one is frictionless and one is friction-y. So which is going to go faster, the frictionless, perfectly slippy, or the one with some friction? I think the frictionless wins, right? So another way to think about it is through conservation of energy. Both of these objects, let's assume for a minute that they have the same mass, and we'll come back to that. The masses will cancel in the end. If they have the same mass, then they start with the same gravitational potential energy. When the box slides down, there's no rotation, so all of its energy goes into 1/2 mv squared, where v is the speed. Whereas with the rolling object, the energy must be shared between 1/2 mv squared and 1I omega squared. It has to have this internal rotation around its center of mass, and that kind of sucks away some of the energy, meaning that the 1/2 mv squared, the v, is less. So it's going to take longer to get to the bottom because the speed is less. And that kind of gets us back to this disk in the hoop, doesn't it? If they both now have to share their energy between translational and rotating, which one is going to suck up more energy into the rotation? The 1/2 I omega squared. The one with the higher value of I. The higher rotational inertia. This hoop has to spin up all that mass that's at the very edge, whereas a lot of this mass of the solid disk is in the middle and isn't as hard to rotate up. And that is why the disk wins. Okay. Now we can do this just dynamics. It's pretty easy. What's the acceleration of a sliding object down a ramp at an inclined angle of theta? So this one, I'm kind of hoping you guys could do this sort of one in your sleep. You'll see, assume no friction. What do? We do define. You do y is up. X is this way. You can draw force diagram, normal force, mg. So don't forget, you're going to have to put your mg into components. So this is mg in the y direction, negative, and this down here is mg in the x direction. There's a theta right there. So F net in the y direction is 0, is n minus mg cos theta. Actually, I don't care about that. I care about the fact that F net in the x direction is equal to m times a, which is going to be mg times sine theta, which is why the m's don't matter. And you get that a is equal to g sine theta. And if you want to evaluate that, it's less than g. Actually, there's two ways. It's less than g, because it's just going down an incline. It's less than 9.8. The other thing I could say about that, to be intelligent, is that as theta goes to 0, so less of an incline, the acceleration goes to 0. If it was a flat incline, it wouldn't accelerate. So like I say, that you should be able to do in your sleep. What is much more difficult is this question. This is really what we're getting at here. But so remember this, g sine theta, we're going to compare that. That's the box. And what I'm telling you is frictionless box is as fast as you're ever going to go. So now you're slowing it down. How does that work? Well, let's start the same way. The only difference is that now you're going to have a torque. So here's your theta. Here's your object. It's going to roll like this. So I'm going to define plus alpha to be clockwise, actually, even though that's not usually done. Same thing as I'm going to put y that way and x this way. Rolling without skidding condition is going to tell us that, I guess, a is equal to r times alpha. I'm going to set rotation axis is the center of the disk, of the solid disk. So now we have to draw an extended force diagram. So the force of gravity, remember, hooks on to the center of mass. So we draw it starting right here, mg. The other force of normal force is down at the bottom, and it's also directed towards the rotation axis, interestingly enough. If you draw a line through the normal force, I hope you can convince yourself that it's going to go through the center of the solid disk, no matter what the angle theta is. Something to do with it being perpendicular here. It's going to go through the center. So, and there's one more force. I think it's the static friction, which is going to be slowing it down, so F static. So the normal force and the mg have zero torque through the center, or something like that. If they both, like the gravity's at the center, normal force is along a line which passes through the center, so those are not acting to rotate it. So all of the torque is coming from the static friction. So the sums of the torques is equal to I times alpha is equal to, I think it's plus F, because that's clockwise, times R times sine of 90 degrees. And I get that I times alpha is equal to Fs times R. So that's an equation. Be careful of my time here. And I've got F net in the x direction is equal to Ma, which is mg sine theta minus F sub s. So the way I'm going to do that is I'm going to take this and combine it. If we call this equation right here equation 2, and call this equation up here equation 3, then if we combine 3 and 1, we get that I times A divided by R is equal to F sub s times R. So F sub s is equal to I times A divided by R squared. And what I can do is plug that into here. Does that sound like a good idea? So then what we get is we get that m times A equals mg sine theta minus I times A over R squared. And we solve for A. We get A times m plus I over R squared is equal to mg sine theta. And we get A is equal to g sine theta divided by 1 plus I divided by m squared, R squared. So, and this is where we use the fact that it's a solid disk, which has I is equal to 1/2 mr squared. You can sub that into there. And you get A is equal to g sine theta times 1 divided by 1 plus 1/2 times mr squared over mr squared, and these cancel. So you end up with 2/3 g sine theta. So this is less than the block. Make sense? So that's sort of the reasoning behind that. And then the last thing I wanted to do was do a soup can race. Sort of out of time here, but I have chicken broth versus cream of mushroom soup. What's the difference between chicken broth and cream of mushroom soup, I guess, is my question. So I think the difference is they both have about the same mass, and They have about the same radius, shape, and all that stuff. But the mushroom soup is this thick, sticky paste with high viscosity, and it's going to stick to the edges of the can. Whereas the chicken broth is just like water. It has very low viscosity and will not stick to the edges of the can. So I want to do it. Let's do a race. Let's put the chicken broth in front. So you'll see that. And the mushroom behind. So this is mushroom. You'll see the chicken broth there. Mark, set, go. Okay. Chicken always wins. So, which is weird. But what I think is going on here, so the answer is going to be, there it is here. It's going to be B. I think that the cream of mushroom soup is like the solid disc. I think that it's so sticky that it probably rotates as 1. And I think what's happening with the chicken broth is it's probably not even rotating at all. If I start up here and release it from rest, certainly the can has to rotate, and it might slosh the soup around a little bit, but generally the soup can almost just sort of slide down. Can you imagine that? And so it's not taking up so much of this rotational energy, maybe a little bit, not much. So have a great weekend, and we'll come back and we'll start in on chapter 10.